All right, so I will say welcome to Live from Behind the Walls. We're glad you can make it. I'm sure a few more people are going to be dropping in. We have 37 people on the list. So before I hand you over to our host and moderator, Alexandros, and our speakers, I just have a few things to take you through. If I can get this slide to work. So first of all, this talk is being recorded and will be posted online afterwards. If you missed some of our previous events, you can watch the recording at the bottom of the page where you registered for this event. And I would like to present the organizing team for this version of Live from Behind the Walls. So we have Alexandros Iosifidis, who is a newly appointed professor here at the Department of Electrical and Computer Engineering. So congratulations on that, Alexandros. And as I said, he will act as our host and moderator and timekeeper today. And Hugo Macedo, who works as a research assistant here at the department. And myself, I'm Lida, and I'm the community manager of Orbit Lab, which is also a part of the department. If you feel like it, you're of course welcome to present yourselves to each other in the chat. And those of you who don't know Orbit Lab, I can tell you that we're a tech and innovation hub, and we're an open community for anyone with an interest in digital technologies and entrepreneurship. So it's students, startups, researchers, and industry. And as I said, we're part of the Department of Electrical Computer Engineering here at Aarhus University. And we also help organize these types of events for the department. And if you want to know more about Orbit Lab, you're of course welcome to reach out. We host a number of other events as well, which we post regularly on our social media channels. So please keep an eye out. And that's it from me. I will now hand over this virtual stage to you, Alexandros.
Thank you, Lita. Okay, so welcome everybody to this sixth edition of Live from Behind the Walls, an initiative we have started to show to those of you who are interested what happens in the area of digital research and innovation with our department. This time, as Lita said, I'm the host and moderator, and in a minute I will tell you about the research we do in the machine learning and computational intelligence group. Before we begin, I have to tell you that this session will be recorded. Here we have today's program. As you can see, we have 9 talks focusing on a diverse set of topics to get through. So I urge the speakers to stick to your time slots and to be ready to take over the screen when it is your turn. Speakers, please turn on your cameras, and everyone else, please turn off yours. Also, please make sure your microphone is muted when you are not speaking. Also, unfortunately, we don't have time for questions during the program, but you are very welcome to type questions in the chat, and the speakers can answer them in the chat after their presentation. Just begin your question with starting with the name of the speaker or the talk title, so that it is clear who should respond to your question. I will start by providing a short introduction to the Machine Learning and Computational Intelligence Group at the Department of Electrical and Computer Engineering of Aarhus University. The Malaysia group is currently formed by 8 PhD students, 1 postdoctoral research fellow, and 1 research assistant. Our work is focused on theoretical and methodological aspects of machine learning, including deep learning, representational learning, artificial neural networks, statistical machine learning, time series, and graph data analysis. Our new techniques and methodologies can be applied to a variety of data-driven analysis problems, and we are currently focusing on problems coming from computer vision and robot vision, financial data analysis, and smart city environments. Moreover, we're collaborating with many researchers and other groups in a diverse set of data-driven analysis problems. With green color, you can see here the research groups from our department that we collaborate with blue color, the research groups from other departments in Aarhus University, and with yellow color, groups from other universities and research institutes with whom we are currently collaborating closely. The topics in these collaborations range from explainable deep learning, distributed deep learning, multimodal data analysis, edge intelligence, meteorology, biodiversity, environmental monitoring, green energy, fluid dynamics, robot perception, financial modeling, digital humanities, digital twins, and industrial process optimization. Our work is financed by externally funded research and development projects, and here we can see the research projects which run in the Malaysia group at the moment. We contribute with our expertise in machine learning, deep learning, and representation learning in audiovisual data analysis to the EU project Multimodal Extreme Scale Data Analytics for Smart City Environments. Arian's talk today will provide more information on our recent work in this topic. We contribute with proposing new deep learning models for robot perception to the EU project Open Deep Learning Toolkit for Robotics. Negar's and Lukas's talks today will provide more information on our recent works in this topic. Also, Illia's talk will provide more information about 3D data analysis in this project. We are among the first to work in advanced deep learning solutions for anti-money laundering. Rasmus's talk today will provide more information on this topic. We are among the drivers in research of financial time series analysis with deep learning models through the project Data-Driven Interstock Predictive Analytics, funded by the Independent Research Fund of Denmark, and the EU Marie Curie Individual Fellowship Project, Bayesian Neural Networks for Bridging the Gap between Machine Learning and Econometrics. Mostafa's and Martin's talks today will provide more information on our work in this topic. Finally, we'll work towards improving the efficiency and reliability of industrial production lines based on machine learning and computer vision approaches in two projects funded by the Manufacturing Academy of Denmark. Moreover, we participate in projects led by our collaborators for proposing new solutions based on machine learning approaches. Here we can see the projects in which I'm a co-PI. For each of these projects, we can see the funding organization and the principal investigator. Most of these projects focus on proposing new machine learning solutions which are able to tackle challenges introduced by the application domain they are targeting for. In the Agile IoT project, we work towards proposing efficient deep learning models for edge computing, including lightweight deep learning and speed computing. In the FlockD project, we work towards proposing federated learning methods for efficient and privacy-preserving distributed training of deep learning models. In the eTouch project, we will work towards exploiting transfer learning approaches for efficient usage of prediction models for haptics. In the BitQ project, we work towards automatic monitoring of the flowering stages of flowers and interactions with visitors, like bees, in flower beds placed in Greenland. This approach can lead to high-resolution analytics that can be used to quantify the effects of global warming. In the Made-Fast PhD projects, we work towards improving the analytics used in industrial process optimization, including anomaly detection, time series analysis, and tool stage prediction. In the Deep Wind Farm project, we work towards proposing physics-informed data-driven models for wind farm flow prediction. Finally, in the AU Digit PhD project, we worked towards proposing new deep learning models which allow for interpreting the results in an intuitive manner. After giving you an overview of the structure and the research topics of the group, we can proceed with the talks given by its members and visitors. Here we can see the list of the invited talks. These are grouped in 4 topics. The first 4 talks will focus on deep learning methodologies for robot vision and smart cities. 2 talks will follow, which focus on industrial time series anomaly detection and environmental monitoring with machine learning. Then 3 talks will focus on financial time series analysis. Finally, I will provide a brief description of our work on other research topics that will not be covered by the other talks given by our speakers today. We will start with a talk on human activity recognition given by Lukas Hedegaard. Lukas, you can share your screen.
All right. I hope you're seeing the presentation.
Yes.
Great, thanks. Then without further ado, let's start. So this will be a sort of high-level introduction to human activity recognition in videos, my current research field while pursuing my PhD here at Aarhus University under Alexandros Iosifidis. So human activity recognition is sort of an umbrella term that's used for many different tasks and settings. Here's an illustration of the problem you might look at. So The images here are of a guy doing a kickflip, but he's doing the kickflip only in some of the frames. So if we had a situation where these frames were pre-cut into a trimmed clip, and the task then was to classify that clip, well, we would name this trimmed activity recognition, to be very specific. Other settings include also identify action proposals. Here we look at when an action is happening, not necessarily stating which action happens, and then temporal action localization and detection, which is what and when. Then to make it even more specific, within each frame, you can also try to detect where the person is doing the action. And those would be the pink bounding boxes here. That setting we name spatial temporal action localization. So while they are different, they all build on the same blocks, and similar architectures are used for all of these settings. Of course, some neural network architectures are specialized to some settings and really shine there, but the same basic principles apply. So I'll be going through 3 different versions or families of architectures that have recently been used to get good results for human activity recognition. And they really treat the video in 3 very different ways. The first one is just looking at the video as a sequence of images. The second one, well, we consider the video as an image, but with an additional dimension. So a sort of 3D image where time is the 3rd dimension. And then a very recent approach is to slice up the video in tokens and make use of some of the recent advances from natural language processing, and to process the video this way. So let's take the first approach, seeing the video as just a sequence of images. So here, the process is as follows. We take an image and we extract some features in space using a convolutional neural network, one pre-trained on image recognition tasks. ImageNet is a staple here. And for those of you who aren't that familiar with convolutions, here's an illustration. The input here is an image, and an image is just a grid of pixels with numerical values. Then what is done in a convolution is that you take a kernel or a filter, and you then slide it over the image. At each position, you multiply the value of the kernel with the value for the image, and then you add them all together. And when doing this, you get an output feature map. And layering this, you have a convolutional neural network. The idea is then that, well, we will learn these filter kernels through backpropagation. All right, that was a quick intro to CNNs. The other part here to make this work is to then use recursive neural networks to aggregate the information over time and to reason temporally. Here is the long short-term memory that's illustrated, but RNNs include different building blocks as well. The idea is that you have an input which you which you feed to the RNN block. It has an output for the time step, but then it also has a hidden state which it feeds back for the next time steps. Here's the same unrolled version where you can see the hidden output is just an input to the same block in the next time step. All right, here are just a few notable works in this family of methods. Here are some for trimmed action recognition, and they performed very well before the big data sets for human action recognition were made available, because they can reuse a lot of the learning we have through images by reusing pre-trained weights. But still, in some settings, they actually are close to state of the art. In settings such as online action detection, where for each, you have an ongoing stream of images, and for each new image, you immediately want to predict what's happening. Here they still work pretty well. All right, so to the second approach, where we just look at a video as a sort of 3D image. You can see here we stack the images, so we have the width, the height, and then the time, and we just insert it at once into the 3D CNN, and hopefully get the correct label out, right? And one of the nice things here is that we can use a very similar architectures to those found in 2D CNNs for image recognition. If anyone has studied deep learning a bit, you might also have heard of ImageNet, and this has really been a driving force to a lot of innovations within visual deep learning. And the same things that have been discovered for images, they do somewhat apply it, or to a high degree even to videos as well. So when you look at the literature, there are sort of pairs where someone made a 3D version of the 2D CNN. Examples are i3D, are just sort of 3D ResNets. There are 3D mobile nets inspired by the 2D CNN of the same name. And X3D is very close to a fission net with tuned hyperparameters. And well, the building block and the main difference here is that 3D convolutions are used instead. So the input here is like a 3D volume, time, width, and height compared with the images here. And the kernel is also a 3D volume that you slide over all dimensions to get an output feature. So let's compare the two for a second, the 2D CNNs and RNNs, and then the 3D CNNs. The 3D CNNs here, they really shine in efficient trimmed action recognition. Here I say that they're still state of the art, even though in terms of just absolute accuracy, not minding the computational cost, transformer style networks are starting to get even higher accuracy. But for efficiency, they're still king in my mind. 2D CNNs and RNNs are pre-trained on ImageNet. 3D CNNs and other video action recognition networks are pre-trained on Kinetics. And Kinetics has been very important because these networks, they really need a lot of data to perform well. And Kinetics is sufficiently large that 3D CNNs took over from this approach. Before Kinetics, 2D CNNs and RNNs were seemingly better than 3D CNNs at that time. Yes, a very big distinction is what the inputs are and how they're treated. So on the one hand, we have predictions per frame, like we take one image and we can actually do a prediction immediately. Whereas for 3D CNNs, you need a whole clip as an input. You need to feed in the whole clip at once. So if we consider, well, can we use 3D CNNs for also doing frame-wise predictions? Yes, we can, but there are some issues, right? We need a running cache of inputs. Maybe I should explain this a bit. At time step 1, here A, B, C, and D are frames, where D is the newest one. So say we have these inputs and then a kernel that we convolve with. Well, it's alpha A plus beta B, and the output is here. And when you convolve the whole thing, you get that sequence. In the next time step, you will need to save some of the frames needed. You discard the oldest one, you add a new frame E here, do the same computation. And what we're getting is actually redundant computations. We can see that the middle parts here are the exact same. So we have additional memory for the input, and also we have computational redundancy. So in a recent work of ours, we have tried to tackle this problem with some success, I might add. And we can't actually compute the same results, the exact same values as a 3D convolution does, but frame by frame. And here's an illustration of the process. So we have the same input D as we had before. If we use zero padding and convolve it, we get these intermediary features. So that was the first time step. Then in the second time step, when we get the E frame from before. We convolve it again, we have new intermediary features, but now we can add up the right intermediary features here. If we add up E beta and D alpha, well, we actually get the same output as we had in the timestep t+1 before. So this saves us a lot of computational redundancy when we're trying to predict frame by frame. And much more information on how this is done in deep neural networks is found in a recent paper of ours. Just to highlight some of the main results here, here's a graph where we have accuracy on Kinetics 400 here on the vertical axis, and the horizontal axis, which is log scale, by the way, shows the floating point operations per prediction, right? So for the square ones, it's per clip, because these types of networks, they need a clip as input, and the circles here, they can do it by frame. X3D, the purple ones here, were the state-of-the-art efficient networks for human activity recognition. And we show in our paper that we can do the transfer from regular 3D CNN to continual 3D CNN and save a lot of computation, like per prediction. So in effect, we can increase the prediction rate by a lot, and also actually boost the accuracy a bit by some tricks we employ. Just to relate this to the newcomers within the human activity recognition field, the transformer style networks, we have a cluster of them up here. So we can see in terms of accuracy, they are very good, right? But their computational complexity is also extremely high. Like this is an order of magnitude going here. So comparing our lightweight methods with theirs, well, it's 4 orders of magnitude in terms of floating point operations per clip. So they have each their usage. All right, but let's cover the transformer style networks briefly. Before we go on, here's just a reference list for interested viewers as to
Lukas,
which. Yes.
2 minutes.
2 minutes, sure. Yeah, a list of some references for 3D CNNs, and here is the hopeful newcomer, our new paper. All right, for transformer style networks, well, what they do is that you in natural language processing, you're working with tokens, which might be the words, right? So we want to slice a video into tokens, and one way which turned out to be good here in the Vivid paper, a recent one, is that they take the input video and they make these volumes, these tubelets, and they then pre-process each of them using a 3D CNN. They get tokens, and then they use the techniques from NLP, the multi-head attention. And this is really a hot topic in deep learning in general right now. So if you're interested, here are a couple of papers that you can start with. All right. So I think we made it in time. I'd like to, well, of course, thank OpenDR project and thank Alexandros. Here's some links for where to find me. And here's a small demo of a continual X3DM network running on a MacBook Pro CPU. And you can see it's fairly fast. And most of the time, the predictions are also pretty good. Like now I'm playing ukulele or guitar, can be hard to see.
Thank you, Lukas.
Yeah.
Let's continue with our next presentation, which will be given by Arian Bakhtiarnia. The topic is audiovisual data analysis for smart city environments. Arian?
Yes. Hi, my name is Arian, and I will be talking about audiovisual data analysis for smart city environments. So smart cities rely on large volumes of data collected from many sensors. So deep learning approaches are a natural fit for processing these information. Our focus is primarily on 2 particular problems, which are crowd counting and anomaly detection. Crowd counting is the problem of counting the total number of people present in a scene. So given an image or video frame of the scene, the output of the neural network is a number representing the count of people. And optionally, a density map detailing the density of the crowd in different parts and pixels of the image may also be provided as the output. Here you can see an image of a crowd from the Shanghai Tech dataset and its corresponding density map. Some of the applications of crowd counting in smart cities includes crowd analysis, video surveillance, and safety and management in stadiums, parades, concerts, and etc. The audiovisual version of crowd counting is where the ambient audio of the scene is also available alongside its image. And this ambient audio can help us in cases where the quality of the image is not optimal. For example, where there is low illumination, maybe it's nighttime, or there's occlusions, meaning that some people are partially or fully covered by an object or wall. Maybe the capture device, the camera is noisy, or the resolution of the camera is not high enough. In these cases, this ambient audio can help improve the accuracy. And here you can see the architecture of CSRNet, which is a deep neural network for this task. The other problem is visual anomaly detection, which is the problem of finding the definition of normality in a particular scene and then detecting any deviations from this normality. So given an image or video frame of the scene, the output is a single flag that says, is this particular frame anomalous? Does it contain an anomaly or not? And optionally, we may also output spatial annotations in the form of bounding boxes or pixel masks. In the left image, you can see a normal scene from a pedestrian walkway in the UCSD dataset. And you can see that the neural network is outputting a regularity score for each frame of the video. And in the right image, there's an anomalous scene from the same dataset where a car is driving on the pedestrian walkway, and therefore it's flagged as an anomaly. Yeah, similarly, the audiovisual version of anomaly detection is where the ambient audio is available alongside the visual cue. And this approach can increase the robustness of anomaly detection when one of the modalities is temporarily not available, or it contains some noise, or when there are cues for the anomaly in both modalities. For example, an off-screen gunshot sound followed by an on-screen crowd dispersing. Now, many smart city applications, including the ones that we just talked about, are time sensitive and have tight deadlines. Moreover, many of these applications are deployed on the edge, either to preserve privacy and avoid transmitting private data, or to avoid delays introduced by the transmission to the cloud. Which means that the available computational resources are more limited because they're running on edge devices. Furthermore, the available time budget and computational resources may vary over time based on the state of the transmission channel, the latency, the bandwidth, and also the input load. Now, all of this means that we need to employ efficient deep learning techniques for these applications. A class of efficient deep learning techniques are dynamic inference methods, which allow the computation graph of deep neural networks to be modified during the inference time for the purpose of increasing their speed when needed, but at the cost of accuracy. And one particular method, dynamic inference method, is early exiting. As you can see here in this image, where early exit branches are added after intermediate layers of the neural network and produce early results. But the problem is, as I mentioned, that these early results are less accurate than the final results. Therefore, in our publication titled Improving the Accuracy of Early Exits in Multi-Exit Architectures via Curriculum Learning, which was showcased in IJCNN 2021 conference, in order to alleviate this decrease in accuracy in early exits, we employ curriculum learning. Curriculum learning is inspired by the way we learn in schools, where a teacher starts with the easy subjects and introduces more and more difficult concepts over time. And similarly, when curriculum learning is used for training deep neural networks, the training starts off with the easiest training examples based on some measure of difficulty, and gradually during the training, more and more difficult examples are introduced to the network. Our other publication, titled Single Layer Vision Transformers for More Accurate Early Exits with Less Overhead, which was submitted to a journal. In this one, we propose a novel architecture for the early exit branches in order to, again, alleviate the decrease in accuracy when using early exits. And we show that it works for multimodal settings, including the audio-visual crowd counting problem that we talked about. And you can see our proposed architecture here in this image. We also introduce a novel way of integrating audio and visual features in early exits. And our other paper titled Multi-Exit Vision Transformer for Dynamic Inference, which was presented in the BMVC 2021 conference, is about early exiting vision transformers. Vision transformer is a recently proposed architecture for computer vision problems that has shown great promise. But the problem is that early exiting vision transformers was not previously explored, which limits its usage in edge computing settings, like the ones that we talked about. So in this work, we provide some architectural recommendations for multi-exit vision transformers, including ones that are trained for crowd counting. And you can see our 7 different proposed architectures in these images. Finally, I would like to mention that our work is part of the Marvel project and funded by EU Horizon 2020. And here's their URL. You can visit them if you're interested. And that's it. Thanks for listening.
Thank you, Arian. Now we will continue with a talk from Negar Heidari on the topic graph classification applications in computer vision.
Okay, hi everyone. I'm Negar, PhD student of the group, and my talk is about graph classification applications in computer vision. And I'm going to present a brief overview of my works in this area. In different computer vision applications like human action recognition, facial expression, or hand gesture recognition, the video data can be modeled as a spatiotemporal graph to represent a sequence of motions, expressions, or gestures. And there are very good public tools available to extract the body poses or facial landmarks or hand skeletons from images. So this kind of data structure is invariant to appearance, viewpoint variations, illumination variations, and so on. And generally, a spatiotemporal graph is constructed from a sequence of graphs through the time, and the nodes are usually 2-dimensional or 3-dimensional, the body joints or facial landmarks coordinates in these applications, and the edges are connecting these nodes spatially and temporally. And graph convolutional networks have been successfully used for graph structure data analysis in recent years. And one of the well-known methods that was proposed for a skeleton-based human action recognition is a spatiotemporal graph convolutional network, or STGCN, and this is the backbone of all our works. This method actually uses the OpenPose toolbox to extract a sequence of skeletons or body poses from action video, and then it has a 10-layer neural network, and at each layer it applies spatial and temporal convolutions on the constructed graph and the feature tensor to extract the needed features for predicting the action. Both spatial and temporal convolutions in these methods, STGCN and its extensions, are standard 2D convolution operations. The spatial convolution actually receives the feature tensor and also the constructed spatial graph as input and updates the node features by applying 2D convolution over the body joints dimension, and then it propagates the features between the body joints by multiplying the resulting feature tensor to the graph's adjacency matrix. So it also employs a learnable attention map to highlight the most important parts of each skeleton for each specific action. And the temporal convolution receives the output of the spatial convolution, and its responsibility is to propagate the features of the body joints through different time steps, again by applying a 2D convolution with a predefined kernel size on both temporal and joints dimensions. Many methods recently have been proposed in this area based on STGCN to improve both its classification accuracy and computational complexity. And there are some drawbacks always in all the methods, also in our methods. So we try to address some of these issues in our proposed works. One of them is that most of these methods process a long sequence of skeletons, around 300, and we argue that there is no need to process all the skeletons in a sequence for each action, and there is always redundant information in a sequence of body poses. So we just need to focus on the most informative ones and select a subset of the skeletons to be processed by the model and predict the action. In this regard, we proposed a model based on the STGCN, which is also equipped with a temporal attention module. And this module employs a learning map to learn attention coefficients for different time steps and selects the skeletons with highest attention scores to be processed by the next layers of the model. And in this way, we reduced the number of floating point operations. And we also obtained some experimental results on the N2RGBD dataset, which is a large scale dataset in this area. And the results show that our method reduced the number of floating point operations by up to 4.5 times, and also the number of parameters for up to 2.5 times, while it has comparable performance or even better performance than the state of the art. The other issue is that these methods use a fixed graph structure, which is initialized by the physical structure of the body skeletons. And for example, for some actions like touching the head, there is no connection physically between hand and head, but we need this connection to recognize the action. So some of the state-of-the-art methods solve this issue by adding a learnable attention matrix to the graph adjacency matrix. So after a few epochs of training, the adjacency matrix doesn't follow the graph structure anymore, so it can model a fully connected graph. So in this regard, we also proposed a solution in which the skeleton graph is modeled as a fully connected graph, and the spatial graph convolution is redefined as a bilinear mapping. So in our new definition of the spatial convolution or bilinear mapping, the attention graph is replaced by a learnable matrix U, which does not need to be necessarily a squared matrix like the graph's adjacency matrix. So we can freely decide on the dimensions of the matrix U, which can be either a squared matrix or it can be used to aggregate all the body joints information or even create a new set of body joints. As an special case, we can set the second dimension of the matrix to 1 so that by multiplying the matrix U with data, the features of all the body joints in a skeleton are aggregated and the input tensor to the next layers only has 1 node per skeleton. So in this way, in the next layers, we will have a simple linear mapping instead of bilinear mapping, which is more efficient. And our experimental results on NTU-RGBD dataset also confirm that by aggregating the node features in the earlier layers, of course, we will have less number of flops, and at layers 6 or 7, we have even equivalent classification performance with the baseline model's performance. And finally, another issue that we addressed is that the baseline method and its extensions usually are based on a deep network with a fixed 10-layer architecture. So we propose to find an optimized network topology for each data set. And in this way, we have less number of parameters and number of floating point operations. So we proposed a progressive SDGCN method, which learns an optimized network topology for SDGCNs by progressively increasing the receptive field size in both spatial and temporal convolution operations. And in an iterative process, the algorithm builds several layers for the model, and at each iteration, the model's performance is evaluated. And finally, the width and depth progression of the model stops if the model's performance converges. And the experimental results also show that the optimized network topology that is found by our method on this data set has up to 7 times less number of floating point operations and up to 15 times less number of parameters compared to the state of the art, while it has comparable performance with the state of the art. This is actually a short demo of my method. The body poses here are extracted by the lightweight open pose toolbox, and the method processes around 16 skeletons per second to predict the action. And finally, since the application of the GCN-based methods are rarely studied on facial expression recognition, in a set of experiments, we just evaluated the performance of the baseline SDGCN and also our proposed method STBLN on 3 facial expression recognition dataset. And we used dlib library to extract facial landmarks from the sequence of images or videos. And we also proposed the progressive version of STBLN to find an optimized network topology for this model. And we also used Monte Carlo dropout to estimate the model's uncertainty for each individual sample. But the application of the SDGCN methods in this area is a bit more challenging because faces are sometimes actively moving, and it is not easy for the landmark extractors to extract the informative landmarks from the images. Thank you, and I would like to mention that this project has been funded by OpenDR European project. Yeah, if you have any questions, please write in the chat.
Thank you, Negar.
Thanks.
Now we will continue with a talk from Illia Oleksiienko on the topic of 3D object detection and tracking.
Hi, my name is Illia Oleksiienko. I'm a PhD student in this group, and my talk is about 3D object detection and tracking. So we have different modalities for 3D object detection and tracking, and there are 2 major datasets. There are new scenes, which has LiDAR, radar, and camera inputs, and Kitty, which is an older dataset, but it's mostly used now. So on the right, you can see an example of point cloud and the corresponding camera image for Kitty dataset. And in red, there are 3D bounding boxes. Those 3D bounding boxes, they show like absolute position in 3D space compared to our ego object, like a car. It's a bit different from a 2D case. So in order to work with such data, there are different methods are needed than just the CNN, because point cloud that we have here is just a set of points. So for example, it can be 30,000 points with 3 coordinates and also maybe some additional values. So the most prospective methods in this field, they work with point clouds, and they use voxelization to structure this point cloud. So one of these methods is point pillars. It's one of the fastest methods. You can operate at 60 frames per second on a good GPU. So what it takes is a point cloud, then it takes a part of it. For example, for Kitty, it's a frontal part. And then we split this point cloud into cuboid shapes and take all points inside a small voxel or a pillar, and then we take features of those points and combine them to represent this voxel. So at the end, these features are combined into one pseudo image, where each pixel represents a voxel in a 3D space. And then those pseudo images are processed by 2D CNNs. So as you can see in the image on the right, that it has some convolutions, some transpose convolutions, and in the end we can predict outputs, predict classes, and 3D positions. Also, this is anchor-based methods, which means that for each voxel we place a set of anchors, and then we classify which anchor should be here if there is an object, and then we take offsets of sizes and positions based on this anchor. So there is a TNet method which is based on point pillars. It's slower, but more accurate method. Also, for security detection, main classes that we have is are car, cyclists, and pedestrians, because those are classes that we can easily extract data from just riding around. So, and TNet is one of the best methods for finding pedestrians, which is much smaller than cars. And it follows the same structure. So we have point cloud, we split it in voxels, and then it has a bit different way of extraction features from those voxels. So it's a triple attention network. So it takes point-wise, channel-wise, and voxel-wise attentions to extract more robust features. And then again, we have a pseudo image, and we have a 2D CNN. But now it's a coarse to fine regression network. So we have this upper part, it's a coarse regression network, and so each which is actually a point pillars CNN, and then we have a bottom part. So from the coarse part we have predictions, and then bottom part, it's a refinery part. It takes features and predictions of previous step and transforms them to make better predictions. So this network, in the end, this network is better at finding objects, but slower than point pillars. So in our paper, analysis of voxel-based methods, so we made an analysis of voxel-based methods such as point pillars and TNet for embedded systems. So embedded systems are those that we use for on robots. So it's like Jetson TX2 or Xavier. So they are very small, and so if we have a very big network, we just can't run it there. And regular networks that can run in real time, like 30 frames per second on desktop GPUs, may run in, for example, 1 frame per second on these embedded systems. Depends on the network and the system. So what we do here is, as you can see on this image, we have green and blue regions. So all together, they are used as an input for a point pillars or TNet. And then so this subscene is segmented so split on voxels. But what we do is we take only half of it. So we have green, which is a near half, and blue, which is a far half, so far subscene. We take only near half of it and then run the network on the near half. And we can do this because it's a fully convolutional network. So shape of an image is irrelevant here. And then we run it here, and we show that if we run network on a near subscene, we have not very big drop of accuracy, and also for pedestrians it's a very small drop of accuracy, but we have a good increase in performance. So if you want to deploy it on an embedded system, you mostly care more about high FPS than a small increase in performance. And also we show that if we train such networks on a near subscene and then try to apply it on a full subscene, it's even better. So sometimes, for example, for pedestrians, 16 near model, it was trained only on near subscene, so it didn't see objects at afar. And then when we apply it on a full subscene, it had higher performance than a full network, which means that training on far objects is not good for those methods. And so they only learn on near subscene and try to apply those features on a far subscene. So here you can see how much FPS changes for point pillars in TNet for different systems like 1080 Ti GPU and also embedded systems, Xavier and TX2. So the best increase is for Xavier and TX2. Yes. And so for 3D object tracking, usually we have few approaches. One is detection-based methods. So this approach takes detections of some 3D object detection method and then tries to associate those detections by some methods like 3D Kalman filter with Hungarian matching algorithm, as in AB3D mod. Also, it's one of the fastest 3D object tracking methods. So it's a pretty simple but efficient one. Also, the second approach is a simultaneous detection and tracking. So we can try to find some either re-identification features, directly regress those from inside of detections, or maybe we can predict like velocity and use velocity match to find matches between future and previous frames. Also, there is a single object tracking approach, similar as for 2D, but for 3D. So in this case, what we do is we have a point cloud. So we have a baseline prediction, so predictions for a frame, for initial frame of an object. We take a point cloud of all points inside that prediction, so as car points of the car, and then we try to find to match this point cloud with a point cloud on the next frame around this object, because we know that object can just teleport around. They have some velocity and it is not very big, so be sure that somewhere around the previous position it should be our new position of an object. And if we match points of a previous frame with some points in a search region of a new frame, we can find a new position of an object, and then for this single object we can track it through consequent frames. In OpenGR toolkit, we create a toolkit for methods that we consider as a baseline, and then we develop. Here you can see a demo image for 3D object detection. So we have two projection. One is from an angle behind, and one is a bird's eye view, and also predictions of objects where they are. And also you can see the code how you can make those predictions. So for each method that we have implemented in OpenGR, we have a learner that you can create and then pass some parameters for it. So you can load pre-trained models if you want to and use them. So here we download a model in a folder models and load this. And then we take point cloud from some point cloud generator. It can be a data set, it can be a LiDAR or something else. And then we just run infer function on this point cloud, and this method should return us a list of predictions in a predefined format, and then we can just and then we can just browse those predictions and have the same result. So it's pretty easy to use OpenGR tools for this. Yes. So and this work has received funding from EU's Horizon 2020 project OpenGR.
Thank you very much, Illia.
Thank you.
Now we will continue with a talk from Blazej Leporowski on the topic Anomaly Detection for Industrial Time Series. Blazej, you can share your screen.
Hi, my name is Blazej Leporowski, and I'll be presenting the part of our group's work focused on anomaly detection for industrial time series. The work described in this presentation has been done during the Smart Industry project in cooperation with robotics companies. The goal of the project was to assess the feasibility of machine learning for anomaly detection during automated screwdriving. The project was focused on cobots, or cooperative robots. Cobots are smaller manufacturing robots that are designed to work in collaboration with humans, hence cobots. And why the focus on automated screwdriving? Automated screwdriving is at the forefront of the general drive towards automation in the manufacturing industry. And around 58% of assembly plants in the US alone implement automated screwdriving in one form or another. And automating quality control, monitoring, and fault detection is a crucial step towards a more effective automated assembly. The first step in the Smart Industry project was to create the dataset that would fit our needs. There are several datasets concerning the process of automated screwdriving available, yet they focus more on modeling the process itself using custom tools rather than the anomaly detection with off-the-shelf components. To that end, we designed and created a dataset with more anomalous samples, complete sensor data from robot and screwdriver, simple, easy-to-use per-event labeling. Per-event means here that every measurement done at 100 Hz has its own label. The code for the gathering setup available online, and the entire process is described in detail in technical report, which, coupled with the use of the shelf components, there is a clarity on how everything was put together and how the data has been gathered. We also provide a supporting Python library that allows for easy pre-processing, for example, different labeling, binary or multi-class anomalies, full or partial motion, filtering. It provides data in form of NumPy arrays or time series generators, and more. As seen in the figure at the bottom left, it is possible to get pre-processed data from machine learning experiments with 3 lines of code. Thus, the ARUSAT dataset is easy to use and well suited both for quick exploratory work and for more detailed use cases, as will be presented next. We performed 3 experiments: multi-class classification in full dataset, binary classification on full dataset, and multi-class classification on screwdriver data subset only. I won't go into too much detail about the results and the numbers, but I will focus on outlining the key findings. In our experiments, we used 2 different models, the TABL, which has been introduced as a lightweight model for time series data. It has been proven to achieve good results on financial time series. And ResNet, which is a household name popular in many areas of machine learning, as previously also mentioned. For full data multi-class classification, we can see that there's a clear difference in F1 scores for different labels. Normal operation missing screw, labeled 0 and 3, are the easiest to differentiate. Assembly component and damaged screw cases, labeled 1 and 2, are harder. On the right, we can see a figure that provides a possible explanation for the differences, one of many. This is a current torque measurement for the screwdriver. On screwdriver data subset only, the differences in labels can still be seen and the best performance worsens. And in the full binary classification experiments, we can see that the ResNet model achieves F1 score that can be actually applied to our use case. And this is the model that is presented in the next slide. Our task for the Smart Industry project was not only to benchmark the machine learning models and assess whether they can perform adequately, but also how feasible the real-time anomaly detection was. A simulation tool, along with a web-based interface, was developed. First, multiple simulations with different data parameters and models have been completed. Then, using this interface, user can browse the results and explore the effects that various filters can produce on the machine learning model's outputs. It was designed to be easy to use for users without machine learning backgrounds, as you can see with the various sliders and windows. The tool presents graphically and numerically the impact post-processing machine learning outputs has on accuracy, number of true positives, false positives, and so on. It also includes the model inference time, which is an important information for feasibility study. Using post-processing, we can optimize for false positives or false negatives, as can be seen in the plot in the bottom left. Depending on the situation, preventing false alarms, for example, or not missing any anomaly, or at least minimizing the amount of not detected anomalies may be more important. So with this tool, you can try to optimize for that. And using ResNet and post-processing, we achieved results that could be considered operational on binary anomaly detection. In summary, by creating a machine learning focused dataset and the simulation interface, we provide a full suite for rapid anomaly detection prototyping. From one-line dataset acquisition to automated and intuitive web-based presentation with exploratory functionality. All elements from the dataset design and gathering process to the final web interface are publicly available and replicatable. We also provide benchmarks for multi-class binary and data subsets using ResNet and TABL models. And a set of pre-run simulations with different models and data characteristics is also provided. As a closing remark, I have to mention that this work was supported by the Smart Industry project granted by the EU Regional Development Fund. Thank you.
Thank you very much, Blazej. Now we will continue with a talk from Jenni Raitoharju. Jenni is a visitor in our university. She is affiliated with the Finnish Environment Institute, and her talk would be on environmental monitoring via machine learning and automation. Jenni, you can share your screen.
Yes, hello everyone. My name is Jenni Raitoharju, and as Alexandros mentioned, I'm a senior research scientist at the Finnish Environment Institute. And right now I'm doing a 3-month research visit here in Aarhus, where I collaborate with both Professor Alexandros Iosifidis and Professor Tuke Höije from the Department of Bioscience. All right, so here are some examples of the environmental monitoring task I'm working on. But in this presentation, I will mainly focus on this first task of taxa identification from laboratory images, because we have done a lot of collaboration in this topic with Alexandros. And we have mainly focused on benthic macroinvertebrates, which are these bugs living in the bottoms of rivers and lakes, and they are very important from the biomonitoring point of view because they can give warning signs of any environmental problems in the water ecosystems. And this is why also the international environmental legislation requires monitoring them. But even nowadays, this identification is carried out manually, and it's very slow and laborious task. So this is why we would like to automate this task. And already many years ago, we started developing this imaging system that takes pictures of this animal falling down in a test tube from these 2 perpendicular cameras. So in this way, we get multiple images from 2 angles of this, each individual. And with this imaging device, we collected first some data. We published 2 data sets, and we also have some unpublished data that we have not been able to use due to some challenges, but the largest publicly available dataset contains almost 500,000 images from 39 taxa. Here are some example images from the first publicly available dataset, and here you can see that for a non-expert, these taxa look really similar, all of them. And also here is the hierarchical taxonomic resolution of the second publicly available dataset. And this shows that for some taxa, even the expert taxonomists were not able to annotate them to the most accurate species level. And this is why some of the taxa are on more low level, either genus or family level annotation. And also this graph shows that the data sets are very imbalanced. So with this initial data collection and identification efforts, we identified some challenges with the tasks. And with in our collaboration with Alexandros, we have first of all focused on the overall classification task, which is very fine-grained, and it has this inconsistent hierarchical labeling, and each specimen has multiple images. In addition to that, we have done a lot of work in this color constancy field, and we hope that this could be helpful also with this varying imaging conditions problem. This is very important because we have noticed that even very small variations like changing the light source can significantly affect the classification accuracy. And this is, of course, something we would like to avoid. And then we have also worked on one class and class-specific methods that we hope will be helpful with these imbalanced classes and also unseen classes, which are, of course, very important from the biodiversity point of view, these rare and future appearing classes. A few years ago, we did this experiment where we compared convolutional neural networks with human experts, even though this was published only last year. This was done some years earlier already. And at that point, the CNNs were not quite matching with the human experts yet. But the interesting observation there was that when these experts tried to do the classification using the same images than the CNN was using, they just completely failed. So they really need their microscopes, and they need to be able to turn the insects around to analyze them. And then recently we have further developed this imaging device. We have now produced multiple copies of this same device, and now we are collecting data sets from different countries that we will then continue working on. And some of the future directions in these topics are that we are trying to automate the whole robot imaging pipeline with the robot arm, and we are also trying to combine this image-based analysis with DNA metabarcoding-based analysis. Here I have an example of another task that we worked on at one point. Here we are trying to detect flowers and different flowering stages in these time-lapse images collected in Greenland. And finally, we recently published this paper in PNAS where we discussed how deep learning and computer vision will transform entomology in various ways. But in general, I believe this holds for environmental monitoring in more general, and there will be many topics to continue this collaboration on in the future. This was all my slides. Thank you.
Thank you very much, Jenni. Now we will continue with a talk from Mostafa Shabani on financial market time series analysis. Mostafa, you can share your screen.
Hello, my name is Mostafa. I'm a PhD student at the EC, and I'm currently working on the financial market time series analysis. So The financial time series analysis is a topic that's related to time series data, and specifically the financial time series data. The prediction for this domain is have some challenges. The main challenges that we have for this type of data is that we're dealing with the high frequency data, and mostly this type of data is depend on the latent variable and also mostly non-stationary. So this make the prediction task for the financial data is a bit challenging. So to tackle this, we have some econometric approaches, which is have some problems, some drawbacks, and also we have some machine learning methods. But currently we are working on the deep learning method, which is the end-to-end learning process. So help us to improve the prediction for this type of data and have a better output for this type of data. So based on this, we started a project named DISPA, which has two main objectives. The first is the learning with attention, which is try to focus on the important part of the data to improve the performance of the prediction. And another objective is the interstock time series data analytics, which is try to predict some certain characteristic of a time series, of the financial time series, based on the information embedded in the other stocks time series. So for this purpose, we use the limit order book data. As you know, these are the stock market trading. So it have a different price and quantity for the ask and bid, and for different levels at a timestamp, and also we have a mid price for each of them. So we use the publicly available dataset FI 2010, and this dataset have more than 400,000 feature vectors. And in this type of data, we try to predict the mid-price change movement, which can be up and down and be stationary. So for the first part that we have the learning with attention, we have some work. The first is the low-rank TABL. As the other also mentioned, TABL is a neural network that has a very good performance on financial time series. So we also use this type of neural network to do our experiments. So this work is depend on the efficiency of the prediction. So we try to use the concept of the tensor low-rank representation to lower the number of parameters and make the prediction, the learning phase more efficient. So by doing this, we have the lower number of parameters. This helps us to have the to improve the time and space complexity, and also without any effect on the performance of the network. So you can see some of our experiment results. As you can see, we have almost the same performance as the original TABL, but with a lower number of parameters. The second work that we have is the augmented TABL, which is based on the question that how we can use efficiently a pre-trained model to a new but similar data set for the time that we do not have access to the old data set, or we do not want to use it because of the size of it or some other problems. So for doing that, we propose a research problem that we have a old task, which is have the old data set, and we train a network based on that. Now we have a new task, which is the prediction of the new stock market data, and we want to generate new neural network based on the old one, which is have a good performance on the both task and the constraint that we don't want to use the data of the old test. So for doing that, we propose the auxiliary weights, which are trained by the new data, and we augmented the old model weight matrices, and we improved the prediction for both old and new data. These are some of our results. So as you can see, the both models are the augmented model, and as you can see, we have a better performance for all the stocks that we have experimented on. The last work for the learning with attention is the concept of using multi-head attention mechanism. So in this case, we try to have a better performance on the attention mechanism based on the thing that is there any possibility to have a better attention part? That means that focus on important temporal events on the data more efficiently or not. For doing that, we propose the stack of the attention mechanism in the network, and then we combine the output of all these attention mechanisms and generate the output. So these are also some results for these experiments, and as you can see, by increasing the number of attention mechanisms, we get better performance for the prediction. So the second objective of this project is the interstock time series data analysis, and the idea is that we want to find a relationship between the multiple financial time series data, and we want to use this correlation for predicting the certain behavior of one time series based on the others. For doing that, we propose a way to quantify the what is meant by the relationship between stocks. So we propose we use a concept of the cross recurrent plot, which is try to bring the data to a new system, and then based on that try to find the similar events in two time series, and based on that it try to generate the line of synchronization, which shows the relationship between two stocks. So this is the output of the cross-recurrent plot, and as you can see, these two events are similar, and we known as the same similar behavior over time. And based on that, we generate this plot, and this is the output of one of our works, which is based on the two stocks time series data. So that's it. And also, this project is funded by the Independent Research Fund of Denmark and the DISPA project.
Thank you, Mostafa. Now we'll continue with a talk from Martin Magris on Bayesian deep learning for financial modeling. Martin, you can share your screen.
Hey, hi everyone. Thank you for hosting this talk. Very nice and interesting so far. So my name is Martin. I am a postdoc in Alexandros Iosifidis research group, and I'm going to provide a brief overview of what is my field and what is the research that I'm doing here about. So as you can see from the title, my research is at the crossroads between econometrics and machine learning. In particular, what it's all about is Bayesian neural networks and applications of these networks in financial context and in econometrics problems. Well, there has been a growing interest in the field of econometrics, which is my background in the last decade of years, because modern data is very particular, has some unique properties. As you know, markets trade virtually in continuous times. There are events happening at a very high frequency, even at a millisecond frequency. There can be multiple transactions and multiple events recorded on an exchange. And this leads to a series of ubiquitous and very particular properties in the financial data that we observe, which are opposed to more classical assumption on which the standard econometric relies that has been developed in the past, for example, for describing and predicting variables on daily data. These include, for instance, the presence of noises, long memory features, which makes the modeling way more complex. Then, of course, there is the quantity of data that is involved, and simple econometrics model, which are highly parameterized and well taught for handling a limited amount of variable struggle. And after that, also it's important to recall that opposed to standard time series frequencies on a daily basis, high frequency time series are by nature multidimensional, and for a given timestamp, well, you record prices, you record quantities, you record the type of event, and thus it seems that machine learning methods are particularly useful and interesting to be used in the context of econometrics. And also, as I read from Mostafa's slides before, he mentioned that the classical econometrics method can suffer of low predictability, suffer from a low predicting ability. And this is not because the methods are wrong or misleading, but because the nature of the data is very complex, and perhaps these methods are not that appropriate on high frequency data. This is a typical snapshot of how transaction, or how the limit order book data, which is the data that is currently recorded on electronic exchanges, looks like. You see, this is a snapshot for a stock which is not very liquid, so where actually you can distinguish the individual entries. There are a bunch of orders cancellation trades happening within very few milliseconds, and this happens on multiple levels, and it's indicating a very complex dynamics where all these parts interact, pulling the price up and down pretty much continuously in time. And so the challenge here is to model the behavior of the price or of the volatility or the joint time series of quantities related to these variables in here with methods that are typical from machine learning. This is very opposed to what econometrics do. Simple models, very rational and well taught for limited numbers of variables, which most importantly are keen to inference from which one you can extract confidence intervals on the prediction standard errors. And here is a little bit of mismatch between the econometric approach and the machine learning approach, where this well, the target is pretty much optimizing the forecasting ability. And here is the idea about using Bayesian neural networks. Bayesian neural networks are indeed machine learning networks, but they offer a series of advantages over the standard artificial neural networks. And these advantages come from the stochastic nature that it's assumed for the underlying parameters, which allows for a full inference once the model is trained on the parameters. In short, the Bayesian neural network is nothing that an artificial network, but stochastic by nature, and is trained with Bayesian inference. There are the classic ingredients of standard machine learning, so a neural network or deep neural network architecture. There is a new element, the stochastic model, overimposed over their parameters, and which have a prior distribution. And this is typical from Bayesian statistic. And then the learning is a bit different because it's done through Bayesian inference rather than simple minimization of an appropriate loss. The model, just to fix the idea, is something that writes down very simple. The output is just the outcome of a neural network, but here the neural network is parameterized over some parameter that has a distributor on itself. And the learning here is all focused on this very famous quantity in all the Bayesian exercises, which is called the posterior distribution. So the distribution that you find for your parameters once the data has been observed and when the learning happened. And this object is the arrival point, what we want to get, what we want to extract. And once we have this, then we can, what follows is all the marginals, so all the distribution of the single parameters rather than the joint. We can extract point estimates like a normal network does, but we can also look at the covariance matrices of the standard errors, and combining all these three ingredients together, we can obtain forecast along with an estimate of where the forecast is going to be, how much the error will be, and uncertainties in general associated with the model training itself and with the forecast. And this is what Bayesian neural networks allow for. And this was very much closer what econometric models do, which indeed they allow to deal with covariances and uncertainties and standard errors. There are, however, a number of challenges. Integration is a typical problem in all the Bayesian settings because you have to integrate over the likelihood, and this is a problem that becomes very difficult already with limited numbers of variables if the distribution are not so called conjugates. But here we deal with deep learning and deep networks where we might have thousands or hundreds of variables. So ideally, we have multivariate integrals over huge dimensions, and this is definitely a problem associated with the training and the research with Bayesian neural network. There are some issues regarding how to set up the priors. If we have two parameters with two priors, okay, maybe we can have some prior knowledge about the initial values of our priors, but of course, in a context where you have 1,000 parameters, the priors are not reflecting any a priori information that you may have. So there is a problem in setting up the prior and studying how the different priors drive the inference. And then it's, of course, a problem about estimation. So how to adjust all the hyperparameters, all the parameters in the network, which are based on the parameters of this prior distribution, and that needs to be optimized based on some criterion. And once finally the posterior distribution is known, then we'll shift to the predictive distribution. And here we have again an integration problem and a sampling problem, which can arise due to the high dimensionality of the parameters involved. And this gets even worse in case where you have very large network or very huge numbers of parameters. So these are challenges. On the other side, the price for solving these issues is that of estimating deep neural network models. And as a part of the estimation, you have the distribution of the parameter, distribution of the output, and so you have the full probabilistic prescription of your object. You obtain forecasts that are not based on some limited or simple econometric model, but on something that has the full flexibility of artificial neural networks for discovering any relationship you may have in your data. And as such, by construction is an extensively data-driven approach. Even the priors are learnable with some techniques that can be used on whatever particular features your financial high-frequency data might have, and can find patterns and interesting relationship in a data-driven and automated approach without superimposing a specific model or a specific assumption. So the forecasting and inference in the context of Bayesian neural networks can happen in very general terms. My project wants to apply Bayesian neural networks for three major problems and three major areas. The first area we're working on is the prediction of the mid-price movements. In particular, we're studying how the mid-price is going to move in time with the associated probability that will go out, stay stale, or move down, change direction or not, based on TABL layers, which has been discussed before. Yes. Thank you. And associated with this is some analysis of the price increment based on a learning which relies on variational inference, which avoids the integration problems. You approximate your posterior distribution with a general distribution chosen in some family, which can be, for example, the exponential family distribution. So it's something rather new, but very interesting. Practically, it prevents you from integrating. You just specify family density where your posterior is likely to be, and then the algorithm automatically chooses the family and optimizes the parameters. And this is something we're working on for finding, for predicting the price movements in terms of ticks from the current price. Related to the research that about stock inter-exchange, stock co-movements that Mostafa discussed before, here we're going to use we're optimizing Bayesian neural networks in the context of co-integrated time series, which allow to develop some trading strategies known as pair trading. And with Bayesian neural networks, we think that it's possible to outperform current strategies, because now we have probabilities that the price will move or not will happen. So this can clearly have an advantage. And a later point is analysis on how we can extend current practices and methods for volatility forecasting in the context of Bayesian neural networks. There has been some external research somehow related to the Bayesian context, but not exactly in the context of Bayesian neural networks here in the bottom. And let me conclude saying that this is a project funded by the European Union. It's a MSCA project. Thank you.
Thank you, Martin. And we will continue with a talk from Rasmus Ingemann Tuffveson Jensen on the topic transaction anomaly detection.
So my name is Rasmus. I'm a PhD student here at Aarhus University. And then for full disclosure, my PhD and the entire project is funded by Sparno Bank, where I am, well, technically also employed. So what I am looking into is, well, the topic here is transaction anomaly detection. What I am particularly looking into is anti-money laundering. So if you don't know this, it might frighten you a little bit, but your bank is definitely watching you. That is for two reasons. First of all, to make sure that your, say, credit card is not misused by a fraudster, but also to make sure that you are not misusing a bank in order to launder money. So this very, very simple illustration is just to kind of explain you the process that's actually happening in a bank. First, an alarm is raised. That's in the left part of the picture. Then it is reviewed by an AML or compliance officer, and then it is either sent to authorities, so the policeman on the picture, or it is dismissed and nothing further happens. And then what I'm looking into is specifically how we can improve this process, and with a focus on the first step. So in particular, right now, you have an alarm generation process in banks where essentially they use if-else statements. So if you deposit, well, if you deposit 1 million in cash in a bank, an alarm will go off and then go on to manual review. But over 98% of all AML alarms, they are false positives. And there are similar results for fraud alarms. So that's a very big problem. There's right now a debate in the industry about whether or not there are actually more alarm reviewers employed in Danish banks than we have policemen. They seem kind of similar, the numbers. And then to kind of also, well, that's probably one of the reasons why the current state is so bad. There's a very, very limited literature on generating AML alarms. It's a relatively new field. And of course, we are also dealing with very, very sensitive data. So not a lot of research can go on, or at least you have to be very privileged to get access to data. Some of the challenges that we're working with in anti-money laundering, first of all, we are dealing with class imbalance. That's kind of like the first line of my PhD project. Fortunately, not a lot of people launder money. That's good for society, but it's kind of annoying when you're trying to do machine learning and statistics. The second problem deals with feedback interaction. So obviously, we only know what we know. We don't know what we don't know in anti-money laundering. That is to say, there's always the possibility that somewhere out there people are laundering money and we simply have no idea how they're doing it. They are actively trying to hide it for us. And then a third challenge that I'm looking into in the PhD is about concept drift. So basically, the concept of money laundering also changes over time. For 10 or 15 years ago here in Denmark, we didn't have phone transfers, phone bank transfers. Nowadays, pretty much everybody uses mobile pay, and that has really changed the way that money laundering is done. So in my PhD, I am very privileged to have a dataset from Spanor. Spanor has over, or just about 400,000 clients. That's quite a lot of data. And my goal is to develop neural network models that simply score all incoming transactions based on past activity. And then this can be used in order to rank and prioritize AML alarms. And this is just some results from my master thesis. It's nothing special, really. I would love to present some cutting-edge research results here for you. I simply don't have them, so you will have to do with kind of like a proof of concept from my own master's thesis. So this in particular deals with the first challenge I talked about, class imbalance. So in order to actually get decent results here from just a simple 3-layer feed-forward neural network that is applied on aggregated monthly features. So it's not even on specific transactions. It's just aggregating all transactions in a given month. And then I looked into how we could balance the data before training, either with synthetic minority oversampling, which basically says, okay, let's generate positive examples, that is money laundering examples, by convex combinations of these money laundering observations, and then random oversampling and random undersampling. And my experiments back then definitely showed that random undersampling was the way to go. But later experiments with just a gradient boosting model also shown that class weights definitely also can be applied. Yeah, so the kind of next step I'm looking into right now, it deals with embeddings and attention mechanisms inspired by natural language processing. Mostafa also talked a bit about the attention mechanisms, and then obviously there's also a big part of anti-money laundering that deals with interpretability and fairness. When we report somebody to the authorities, it's nice to be able to explain why they were reported. And this also needs to be incorporated into any machine learning models. Yeah.
Thank you, Rasmus. After all these interesting talks, which provided details of our work in different aspects of machine learning and its application in different problems, I will close this webinar with a quick overview of other contributions we have made during the last couple of years. Most of the works that I will show are the result of our interaction with the research groups we collaborate with. With our collaborators in Tampere, including Dr. Jenni Raitoharju, who gave a talk earlier today, we have been working towards two very interesting applications of machine learning. The first one is automatic estimation of social distances through non-invasive means. This is a problem which drew attention lately, and there is a lot of room for new contributions. We proposed a new methodology and introduced a new dataset along with an evaluation protocol for measuring the performance of the methods in this area. The second one is semantic analysis of historic image archives. With this work, we hope to assist researchers in humanities and social sciences to automate the processing steps required for their statistical analysis over large image archives. Moreover, in the near future, such semantic annotations will be a requirement for public image archives in Europe due to a recently introduced EU directive. Two recent contributions in image analysis and synthesis are the introduction of a new GDPR-compliant dataset for illumination estimation, along with an efficient methods for this problem, and the proposal of a new methodology for evaluating the performance of methods that are able to create new images that depict the contents of a free text provided in their input. In one of our industrial PhD projects, we worked towards improving satellite-derived solar irradiance nowcasting based on specialized deep learning models. The ability of having accurate solar irradiance forecasts is very important, as in a power grid that has a considerable percentage of renewable energy, there is considerable due to solar energy fluctuation nature. Moreover, we worked towards improving performance of cloud forecasting and introduced a large-scale, high-resolution dataset that can be used for methodology development and performance evaluation. From the neural networks methodology side, we recently introduced a new class of neural networks that are able to better model complex nonlinearities compared to existing neural networks formed by homogeneous layers composed by affine transformation-based neurons. Moreover, we proposed new methodologies for efficiently training such complex neural networks, leading to compact and high-performing neural network structures. Moreover, we proposed a new methodology for determining the neural network structure for analyzing medium-sized graphs, leading to high-performance solutions requiring low human experimentation. From the statistical machine learning side, we proposed new methodologies for anomaly detection using unimodal and multimodal data, along with a theoretical analysis of the properties of this new class of novelty detection methods, combining subspace learning and one-class classification. Moreover, we proposed new techniques for single view and multi-view ranking problems. We propose new methodologies for adaptive multi-domain learning, transfer learning, and few-shot learning. These methods have been shown to provide state-of-the-art performance while leading to efficient solutions or simplified interpretation of their properties. We were the first to introduce the multilinear compressive learning framework, which has a very nice fit to Internet of Things and edge artificial intelligence. Moreover, we proposed a new interpretable deep learning model and a new protocol for the evaluation of interpretable deep learning models, which we believe provides a more complete quantitative evaluation of the different interpretation properties of deep learning models. We recently analyzed the properties of the widely adopted attention mechanisms used in deep learning-based image classification, and we proposed the idea that sometimes it is easier to learn which parts of the image the network needs to ignore in order to provide a higher performance. Intuitively, this makes sense, as many times it is easier to determine which parts of the image belong to the background and thus exclude features from these image locations when classifying the contents of the image. When working with deep learning for financial time series, several challenges arise. One of the biggest challenges is how to perform effective time series data augmentation. While this process is easy for image data, the time dependencies in time series data make it difficult to provide an effective methodology. We proposed two new methods which were shown to consistently improve performance while being easy to implement in a wide range of deep learning models. Moreover, we analyzed the effect of using multiple limit order levels in the data when performing stock mid-price direction prediction. Our analysis showed that, contrary to most recent financial econometrics research, where only the first limit order level is used, when using deep learning models, we need to include multiple limit order levels to achieve high performance. Finally, we can see some of our more theoretical results on the generalization ability of deep learning models, where we showed that increasing the within layer diversity, we can improve the expectation of the model's performance, and that deep learning models, the parameters of which are estimated by using error backpropagation-based iterative optimization, inherently improve class compactness at their last layer. This is the layer which is used in order to classify the input. So we showed that these models can inherently improve class discrimination in their input data representation. Thank you, everyone, for being here. If you want to join us next time, you can see the future dates here. The event will be announced via the event section on our department website, which is ec.au.uk. And those of you who registered for this and the previous events will also get an invite via email. Also, thank you to all the speakers for presenting your work. If any of you in the audience are interested in learning more or getting in contact with one of the speakers, we will be happy to assist. And you are welcome to get in touch with any other questions or comments as well. You can see the contact details of mine and Lites in this slide. That is all for now. Thanks again for joining, and see you next time.